Hello everyone, welcome to SIGCOMM' 2022 preview session. I'm Yuanjie Li from Tsinghua University. In this video, I will preview 5 exciting papers this year in sensing and wireless communication. I'm going to give you some background and context to help you understand and appreciate this great work in this space. We are living in a wireless world. Today, we are surrounded by numerous wireless signals, devices, and sensors. Wireless technologies have been the foundation for many sensing and communication systems. They have empowered numerous applications such as virtual reality, underwater communications, indoor localization, RFID, vehicle networking, and many more. In general, these wireless applications can be classified into 2 categories. The first one is wireless sensing, which leverages the wireless signals to monitor and record the physical conditions of the environment. The second one is wireless communication, which leverages wireless signals to transmit information between nodes without cables. So, how does it work in general? Well, the first step for wireless sensing and communication is to create wireless signals. The wireless signals can be any time-varying electromagnetic or mechanical waves that carry information. The information can be carried by the amplitude, frequency, or the phase of the carrier wave. Today, most wireless sensing and communications are based on the radio signals or acoustic signals. The radio signals use electromagnetic radiations. They are created by alternating current at a desired communication frequency. The acoustic signals use mechanical waves. They are created by the mechanical vibrations. Once the wireless signals are created, they will propagate from one location to another. The radio signals can be propagated in vacuum. The acoustic signals must be propagated through mediums such as gases, liquids, and solids. In this process, the energy of the wireless signal will attenuate for at least 3 reasons. Number 1, since the waves radiate in all directions, their power will attenuate. This is called path loss. In free spaces, the received power density attenuation is inversely proportional to the square of the distance from the sender. Moreover, wireless signals can also be absorbed when propagated through materials. How much energy is absorbed depends on the medium materials and differs between the water, metals, and walls. Number 2, the obstacles between the transmitter and receiver attenuate or even block signals through reflection, scattering, and diffraction. This is called shadowing. Whether a signal will be blocked depends on its nature, its frequency, and the materials. For example, the radio signals can be totally blocked by the metals due to Faraday cage, while the acoustic signals may not suffer from it. And lastly, signals can reflect off different things in the environment like walls and floors. The same signal may propagate through multiple paths and combine at the receiver. This causes multi-path fading. In general, the path loss attenuates very slowly, while the multi-path fading incurs more frequent signal strength fluctuations. To characterize all these effects, the communication theory defines wireless channels to describe how radio signals from the sender propagates along multiple physical paths and combine at the receiver. The characteristics of the wireless signal propagation heavily depends on the carrier frequency. In general, the higher the carrier frequency is, the more capacity we would have. But the cost is the faster attenuation and thus smaller wireless coverage. Therefore, we face a trade-off between the wireless coverage and performance. For example, the acoustic signal ranges between 20 Hz and 200 kHz. So, it's good for long-range propagation, but at slower data rates. The radio signal usually ranges between 3 kHz and 300 GHz. So, it has fast data rates, but relatively smaller coverage. Now, the question is, how to use wireless signals for sensing and communication? Let's look at each category. To sense the environment with wireless signals, we leverage the fact that the wireless signals will reflect off the objects and refracts when it travels through a boundary between two different materials. For example, the wireless signals will reflect off our bodies. So, if there's someone standing behind the wall, a very small fraction of his reflections will come back to us through the wall. In this way, we can use sensors to capture these reflections, correlate them with specific patterns, and then accurately infer where the people are, how they are moving, and even their heartbeats and other health metrics. Wireless signals can also be used for communication. Today, we are all using many wireless communication technologies, such as Wi-Fi, cellular networks, Bluetooth, RFID, and many more. In general, they can be classified into two modes. The first mode is active communication. In this mode, all wireless nodes are self-powered by batteries or cables. They use their own energy to generate signal waves for information transmission. This is how the legacy Wi-Fi, cellular network, and Bluetooth work today. The second mode is passive communication, or backscatter. In this mode, some wireless nodes do not have battery or external powers, so they cannot actively generate wireless signals. Instead, these nodes harvest energy from the environment or other signal sources, and then they reflect these signals with their own information. One example for backscattering is the radio frequency identification, or RFID. The RFID tag has no battery. It reflects the signals from the RFID reader to transmit digital data back to the reader. Compared to the active communication, the passive backscatter communication is more friendly to low-cost, battery-constrained Internet of Things. As users, we have many demands for the wireless sensing and communication. We want to enable sensing and communication everywhere, not only over the air, but also in the water, through the walls and metals, and even in the space. We want our wireless links to be as fast as possible to support new applications such as virtual reality. We want our wireless sensing to be secure and private, given that we have been surrounded by many wireless signals whose reflections may unveil our private information. And we want our wireless sensing and communication to be energy efficient, with as little battery use as possible. Of course, in reality, we may not be able to achieve all of them simultaneously, so we have to make some trade-offs. How to balance these demands depends on the specific user scenarios and environment. This stimulates many exciting research challenges and opportunities. This session has papers that cover all these aspects in diverse wireless sensing and communication scenarios. We'll see papers that explore new wireless sensing application domains and protect our privacy against malicious sensing. We can also see papers that enable affordable and performant wireless communication in the water, through the metals, and for the emerging virtual reality applications. In the following, I'm going to go through both aspects and highlight the contributions of each paper. Let's start from the wireless sensing. The first paper explores a new application domain of wireless sensing called the structural health monitoring. Today, the number of building collapse tragedies keeps growing due to the earthquakes, tornadoes, and even wars. People gradually recognize that long-term and persistent structural health monitoring becomes important for civilian buildings. It helps ensure the integrity and safety of the buildings, detect the evolution of damage, and estimate performance deterioration of civil infrastructure. However, current structural health monitoring suffers from high cost and deployment difficulty caused by the wired connection. Traditional wireless sensor networks fail to serve in concrete communication for structural health monitoring because of the complexity of battery replacement and the concrete Faraday cage. To solve this problem, the authors collaborate with experts from civil engineering to create a non-intrusive, battery-free piezoelectric backscatter node. They have overcome the fundamental challenges in concrete energy harvesting and wireless communication for structural health monitoring. The authors have also tested the solution regarding real-world buildings comprehensively. From this paper, you can learn how to leverage piezoelectricity to enable in-concrete backscattering, and how to enable in-concrete energy harvesting and wireless communication. The next paper is concerned about the privacy threat of the malicious wireless sensing. Today, low-frequency RF sensing systems have the ability to penetrate through walls and obstacles, making them a great privacy threat. Using RF sensing systems, a curious neighbor can track whether you are at home, when you go to bed, take a bus, wake up, and other daily activities by simply deploying a sensor next to the wall. The bad news is that there's no easy way today to avoid this problem. Traditional solutions rely on jamming the radio spectrum, which however will disable communication on user devices and can sometimes be illegal. Another solution is to convert homes into Faraday cages with metals. This avoids wireless signals from propagating from one home to another, but it also limits other legal signals of interest like cellular signals to operate in homes. To solve this problem, this paper proposes a new framework that enables privacy by injecting fake humans in the sense data. This system doesn't make humans disappear, but fills up a home with fake humans that prevent accurate inferences about the state of a home. To achieve so, it develops a new hardware reflector that generates fake customizable reflections in the environment. It also leverages machine learning to control the reflector to ensure that these fake reflections mimic real humans. For more details, please read the paper and attend the presentation. Now, let's look at the wireless communication part. We have 3 papers this year on different aspects of wireless communication. The first paper studies underwater communication with our commodity phones. Unlike over-the-air wireless communications, the underwater communication has very different channel models. The radio signals we use today, like Wi-Fi and cellular, are not suitable for underwater communication due to multibus fading and delay spread. For example, the 2.4 GHz Wi-Fi signals can attenuate as much as 169 dB per meter in the sea water. To this end, the low-frequency acoustic signal is a more viable choice for the underwater communication. However, current custom underwater acoustic hardware is very expensive and cannot scale. This paper offers a software-only solution for these issues. It uses microphones and speakers that are readily available in today's smartphones to enable acoustic underwater communication between mobile devices. From this paper, you can learn how this solution adapts to differences in frequency responses across mobile devices, changes in multipass and noise levels at different locations, and dynamic channel changes due to mobility. The next paper studies acoustic communication through metals. As we know, the radio signals can be shielded by metals. For applications like structural health monitoring and in-body communications, the acoustic backscattering is a more viable choice. However, the acoustic backscattering suffers from low data rates. When backscattering, the tag has little control over the modulation it performs on the carrier wave. Therefore, existing approaches commonly employ differential binary modulation schemes, limiting the achievable data rates. To overcome this limitation, this paper first derives a channel model in metals that accurately describes the modulation in the acoustic backscattering. Then, it leverages this model to achieve higher order modulation that covers up to 3 meters and achieves up to 2 times higher data rates than binary modulation schemes. From this paper, you can learn how the wireless channel model in metals differs from the legacy ones, and how to enable higher order modulation for backscatter communication. The last paper studies free space optical communication for virtual reality. Virtual reality is an exciting technology that creates a simulated environment within which the user becomes fully immersed. To achieve so, the VR headset should stream tens to hundreds of gigabit per second data to provide a true, lifelike, and immersive experience. Recently, there has been strong interest to create wireless VR headsets in the industry as well as the research community. However, this is difficult due to the fundamental bandwidth limitations of low-frequency spectrums in today's wireless technologies. To circumvent this bandwidth limitation, this paper uses free-space optical technology to build a wireless VR link. Free-space optical links can provide high data rates due to high frequencies of the light waves and narrow beams. The challenge is that with narrow beams, the optical links have line-of-sight requirements that is vulnerable to user movements. To this end, this paper develops a tracking and pointing mechanism that maintains the optical link continuously. From this paper, you can learn how this can be achieved by leveraging machine learning techniques. So in summary, there are many interesting problems in the wireless sensing and communication. I hope you will enjoy the paper talks, ask questions during the sessions, and find more exciting problems to work on in this space. Thank you very much, and hope you will enjoy this session.